So this is the section 8.1, parametric equations and arc length. It's kind of lengthy, so just kind of bear with me here. All right, so parametric equations. So we want to recall that a relation is a set of ordered pairs, x, y, of real numbers. The graph of a relation is the set of these points in a plane that corresponds to the ordered pairs of the relation. So think about anything. Don't think of just functions, because it can be, the graph can cross itself and all that kind of stuff. That's a relation. And so because it's not necessarily a function, it's difficult for us to do problems with them. And so what we're going to do is we're going to define the coordinates x and y as functions. So x is going to be a function and y is going to be a function of a third variable t called a parameter. And so that's what's happening here. So if x and y are given as functions, x is f of t, y is g of t over an interval of t values, then the set of points x, y are equal to these things right here, which are individual functions. These functions, this thing is called a parametric curve or a plane curve. The equations are called parametric equations. So these are parametric equations for the curve. The variable t is a parameter for the curve, and its domain is the interval I. Sometimes they'll give you a specific interval, and sometimes they'll give you the entire number line for t. It just depends. A lot of times they'll do it based off of a closed interval. Your calculator will do this, and we'll talk more about that in just a little bit. So if I is on the closed interval, then this point is the initial point of the curve, and f of b, g of b is the terminal point of the curve. And the curve itself will have some form of direction. It'll start here and travel until it reaches the other point on the curve, the last point on the curve. And so that's kind of important when you start talking about vectors and things like that. So note, the parametric t is not always defined on a closed interval. It can be defined on the real numbers, but the graphing calculator will define t on a closed interval. So what I just said. So let's take a look at this. First little example here is we're going to graph this plane curve, okay, given those two parametric equations. So let's see how we go about doing that. So here we have it over here, and what you're going to do is you're going to want to make a table if you're doing it by hand, okay, and then I'll show you how you can type it into the calculator itself. So here's some t values. Again, I didn't define an interval for t, so we can just we can do all real numbers for t if we wanted to. So just with these numbers right here, we plug it in. Here's t squared is what x is, and t to the third minus 2t is what y is. So we're going to plug all these numbers in. If I plug all these in for t squared, this is just going to be 9 and then 4 and then 1 and 0, 1, 4, and 9. Pretty straightforward. And then you plug in this -3 into this expression over here to get the y values. And you can figure that out here, but you know, taking -3 in here in cubic, that's -27. Put a -3 in here. That's going to give me +6. So -27 plus 6, -21. And you can see how that works for all of these. So I have these values right here. Okay, so what points am I graphing? Well, I'm graphing the x and y points. X is 9, y is -21, and so forth and so on. So let's graph the ones we can see. When x is 0, y is 0, so we have a dot here. And when x is 1, y is -1, and also +1. So when x is 1, we have a dot here at -1 and a dot here. And we continue on. 2 gives me 4, 4. And 4 gives me -4. Nope, I put it in the wrong spot, excuse me. 4, 4 is the point I want. And 4, -4 is the point I want. Clearly this one's going to be too big for us to do, so we know that it's going to keep on going upwards. So it's kind of hard to see this, what it looks like. You may think it just does something like this and like this, but there's actually a big loop here in the middle of it. Okay? And we can explore that in more detail, but let's use our calculator to see what this graph looks like. So when I turn on my calculator and go to a graphing page, which is I'm at right here, all right, I want to graph a parametric equation. Let's see if we can see them. And so go to menu, and you'll see graph type number 3. And if I go across here, you'll see all the different kinds of graphings we can do. There's parametric and polar, the things we're going to be talking about in here. You just go down to parametric, and it will change this down here. It gives you a place to type in your x function, your y function of t. So make sure you type in the variable t when you do this, and also the interval. So you can change this interval down here to whatever you want it to be. Okay? And so don't leave it as there. You're going to have to change it. So we need t squared. So find the t and square it. And then we come down to this one, and we have t raised to the 3rd power minus 2t. Okay? And then we come down to these, and you're going to need to scroll back over here and just change these values. What do I want t to go through? Well, clearly I have it from -3 to +3. Okay? So let's just do -5 and back this up and go to +5 and see what this graph looks like. You can leave the step function there itself. You can change that one also. It's gonna plug in 0.13 each time for t and to get their points. If you want it to be a little bit more consistent, just go to the nearest tenth, so 0.1, and hit enter. Okay? And so that's what we're looking at right there. And I need to get this out of my way. And let me go look back at my function again, because I think I didn't make that a -5 on the one side, because it's not giving me everything. And I can't go back to it. So let's just do another one. Type it in again. When I did the one before, I forgot to put -5 on the step function over here, and so it only gave me the bottom half. It didn't give me the top half. And minus 2t. We'll go to 5. And this one's -5. There we go. So we just graph it again. There's the other half, so the bottom half of it. So that's what our graph looks like. So if you look over here at our picture we had, there's a point right here where they're going to cross on the x-axis. So there is a point where these two things here are equal. And you can solve that out, and you can do it on the calculator, and you figure out, and you'll find out that it's going to be, I think it's at square root of 2. Okay, and if you look closely at it, you can see it's somewhere right about 1, or right there. So we know what this thing is doing is it's coming down through here, and then it's curving around and then coming back down through here. And that's what that graph is looking like. Okay, so you can use the calculator for parametric graphing, which is most of the time what they'll have you do on this calculator as we go. And when you do your first assignment in the homework, you'll be asked to change to Cartesian equations. These are just simply XY equations. So if this is the parametric, what does the XY equation look like? The Cartesian equation, okay, or rectangular coordinate points. Things, they'll use those terminologies. And so the key to this is you take one of these equations and you solve for t, and then you substitute into the other one. So you're solving a system. So if I take x, which is 2t minus 5, and solve for t, I'm going to get t to be x plus 5 divided by 2. Then take that quantity of t and plug it into that one. So y is going to be 4 times t, which is now this, minus 7. And then you just solve this out. This 2 and that 4 cancel. It gives me 2 times x plus 5 minus 7. And then I can solve this equation and get 2x plus 3, 10. And so this equation can be expressed as a parametric equation in that fashion. Okay? Let's look again at another one. Let me move this camera so we can see it. So in this one right here, find the Cartesian equation for the plane curve defined by the parametric equations sine and cosine, so that you can see one that's done with the trig functions. So the process I do is what? Well, normally I would try and solve for t, but these are trig functions. So in trig functions, you want to kind of base it off of a trig identity. So do we have any identities that contain both of these? And the answer is yes. And you think of the main ones. So think of your Pythagorean identities and your inverse ones, your reciprocal ones, your quotient ones, your main ones right there. Okay? And so because I do have that, I know from the Pythagorean identity that the sine squared of an angle plus the cosine squared of an angle is equal to 1. So I know that already. That's an identity. Well, if sine is y and cosine is x, well, sine squared then must be y squared, and cosine squared must be x squared. And so there I have my equation there. Okay? So that's how that works. So here's some other information here that we're going to be looking at to the next round. And you can see right here, I forgot to let you guys copy that down. So that's the equation. Here's a little side notes over here that I said. Okay, and so then let's look at this right here. Now we need to get started with differentiating parametric equations. So how do I take the derivative? Okay, to do that I need to have a definition of what is a smooth curve. And so let's go ahead and take a look at that. Let C represent a plane curve. So this is a curve that's in the plane, xy plane, defined by the parametric equations. X is x of t, y is y of t, for t between a and b. Suppose each of these functions is continuous on the closed interval from a to b and differentiable in the open interval. If both dx dt and dy dt are continuous and never simultaneously zero on that interval. So they each can be zero, but they both can't be zero at the same time. Then C is called a smooth curve on that closed interval. So how do I find the slope of a tangent line, which is basically this? How do I find dy dx? So literally it's right here. To find dy dx, it's the derivative of y with respect to t divided by the derivative of x with respect to t, as long as this bottom one is not zero. Okay, so this is how you're going to take the derivative in parametric mode, right there. That's your key thing. So we have an example coming up. Let's go ahead and take a look at it. Yep, right here. So consider the parametric equations. X of t is the cosine of t and y of t is the natural log of t. Find dy dx. Okay, so I recommend that you do it just like this every single time. Dy dx is dy dt divided by dx dt. Please write it this way. And then find your derivatives. Don't try and go right to the derivative stuff. It's just going to confuse you later on. If you do this, when you do later derivatives, second derivatives and stuff, it's a lot easier if you do it this way. So dy dt, so what is the derivative of the natural log of t? Well, it's just simply 1 over t. What is the derivative of the cosine? It's a negative sine. And so you can clean this up into a nicer fraction, and you literally get a negative 1 over t times the sine of t. And there you go. That's how it works. Okay? Let's look at the next thing that I have. So we have some parametric equations. So x is t squared and y is this t cubed minus 2 again. Find the equation of the line tangent to the curve at t equals 1/2. Okay, so as always, what do I need to know to find a tangent line equation? I need a point and a slope. Okay, I need an xy point and a dy dx is what I need. So let's find our point. Our point is found when t is equal to 1/2. So what is x at 1/2? And we can figure this out. You plug in the 1/2, you get 1/2 squared, and you get 1/4. Okay, let's find our y at 1/2, and you'll get 1/2 cubed minus 2 times 1/2, and you work this out, and you're going to get a negative 7/8. So my point is 1/4, negative 7/8. So that's the point. So now I need the slope. The slope is dy dx. dy dx is dy dt divided by dx dt, and dy, the derivative of y of t, is 3t squared minus 2. Okay, and dx dt is going to be 2t. So I need to take this quantity right here, the dy dx, and evaluate it when t equals 1/2. So this is going to give me 3 times 1/2 squared minus 2, and 2 times 1/2, so the bottom is just going to be a 1. And you work all this out, and you're going to end up with a negative 5/4. So now that I have my slope and my point, I can write my line equation. My tangent line is going to be y minus, and then you put y equals, the y value, and then the slope times x minus the x value. So this is how I would write it right there. Okay. All right, so let's look at another example that I have that you may be asked to do. Little pear-shaped graph over here. This up here is like 10, this is 3, this is negative 3, and so on. So consider the parametric equations. X equals 3 sine of t, y equals t squared, where t is between negative pi and pi. The graph is shown. 2 parts. The graph intersects itself at 0 pi squared. For what value or values of t does this occur? And the second part is, find the points where the tangent line to this graph is either horizontal or vertical. Okay, so we have a lot going on here. So let's go ahead and work this out. Let's start with the first part. Let's solve A. The graph intersects itself at 0 pi squared. For what value or values of t does this occur? Okay, so if it's this, then that is the x and that is the y. So that means x of t is 0. X of t is that, so 3 times the sine of t is 0. So the sine of t is 0. And so what values of sine is going to give me a 0? Well, when t is equal to some constant number times pi, okay, for k is an integer. So at, so at 0 and pi and 2 pi and 3 pi and 4 pi, so, and negative pi and so forth. So when k is an integer, this will produce a 0 in this one. Well, what about y? Y of t is pi squared. Well, y of t is t squared, so t squared is pi squared. So be careful when you do this. You're going to square root both sides, and when you take the square root, you have to put a plus or minus pi. Okay? So what values of t satisfy both of these? Well, this does, right? So we have 2 values So the values of t that satisfy both equations are when t equals plus or minus pi. So those are the two values where that occurs. Okay? So that is the A. The next one is find the points where the tangent line to the graph is either horizontal or vertical. So you kind of get an idea where this is going to occur. The horizontal, you can see, is going to be probably down here. And the verticals are going to be on these outside edges here somewhere. Okay? And so we have to find those points where that occurs. I think we can find one of them fairly easy, but let's go through the process that you're going to follow. I got to turn this over. So part B. So the first thing I need to do is I got to find the derivative. Since we're talking about slopes of tangent lines, I need to find the derivative of this function. So what is dy dx? Well, that's dy dt divided by dx dt. And dy dt, remember, is t squared, so this is going to be 2t. And then the other one was 3 sine of t, so the derivative of that would be 3 cosine of t. So that is my derivative. I will have a vertical tangent, okay, when dx dt is equal to 0, because then the slope will be undefined, right? And I'll have horizontal when dy dt equals 0. And I don't have a definite, it may occur. So may, I forgot to write that, may occur. And again, horizontal may occur. There's always exceptions to all kinds of rules, so just got to be aware that, but we still follow this process. So when is this thing equal to 0? Well, dx dt, which is 3 the cosine of t, when is that equal to 0? Well, that's equal to 0 when the cosine of t is equal to 0. And when does that occur? Now remember, I don't know if you remember, t is between negative pi and pi. So in this interval of t, when is this going to happen? When t is equal to plus or minus pi over 2. Okay? So if these are the t values where I could possibly have a derivative on the bottom equal to 0, where it's undefined, a vertical tangent, then I need to find those points where this may occur. So what is x at pi over 2? Let's figure what that is. And let's figure out what y of pi over 2 is. So x, if you remember on the equation, x was, x of t is 3 times the sine of t, and y of t is t squared. So plug in this, so you get 3 times the sine of pi over 2. That's 1, that's 3. Plug it in here. Pi over 2 squared, pi squared over 4. So this point is 3 pi squared over 4. But we also have to do it for negative pi over 2. So 3 times the sine of a negative pi over 2. This is a negative 1, so this is negative 3. This will still be the same value of pi squared over 4. And so this point is a negative 3. So those are the 2 points where I have a vertical tangent. For the horizontal tangent, same process over here. dy dt, which is t squared. Okay, when is that equal to 0? Well, that's going to be equal to 0 when t equals 0. So what is x at 0? Well, that's 3 times the sine of 0, which is 0. And y of 0, which is 0 squared, 0. And so we already kind of knew this was where it was going to be. I will have a horizontal tangent at the origin 0, 0. So this is the process you're going to be following for this. Okay? Let's look at another type of equation, or a problem that might be asked to do. There's a parametric equations. We got x of t is t cubed minus 12t plus 8. Y of t is t squared minus 4t plus 5. T is between negative 10 and 10. Find the points where the tangent line to the curve is either horizontal or vertical. So it's the same type of problem again. And so let's go ahead and look at this process. So if I'm looking to find tangent lines, horizontal or vertical tangent lines, that's the slope. That means we need to find dy dx. dy is dy dt, dx dt, and we find their derivatives. So dy dt is going to be 2t minus 4. Down here we're going to get 3t squared minus 12. We do some simplification right here. I'm going to take it all the way out here so you can see it. I'm not going to reduce anything. This right here will be 3, and you'll see that it's going to be this right here, t plus 2. I'm not going to reduce these common factors, but I'm going to point it out to you in a minute, what's going on. Okay, so vertical may occur when the denominator, right, is equal to 0. So when is dx dt equal to 0? And we can see right here, dx dt is going to be equal to 0 when t is equal to plus or minus 2. Okay? Horizontal, we need dy dt equal to 0. So then we have up here on top, when is that going to happen? When t is equal to 2. So what happens here is this. Dx dt is 0 at positive 2. Dy dt is 0 at positive 2. And one of the things, the conditions we had before is they cannot both be 0 at the same time. Okay? So because they are both simultaneously 0 at t equals 2, we have neither a horizontal tangent line nor a vertical tangent line there. Okay? And you can also see here why that's going to occur, because this t value comes from this common factor and it reduces out. Okay? But just note that's why you cannot have that simultaneously one. So we have only when we have t equals negative 2, and so we can find the point where this is going to occur. So plug it all in, and minus 12 times negative 2 plus 8, that will give you 24, and you can work out all this and double check my math for me. Negative 2 squared minus 4 times negative 2 plus 5, and 17. And so we will have a vertical, because that's the only place where, okay, is in a vertical tangent. We have a vertical tangent at the point 24, 17. Make sure you write it out that way. Okay? You have to explain exactly what it is that you have. Now I'm going to show you some side notes here so you can see how this came about and some of the stuff that I wrote down. So here's the problem I just did, and here's a little side notes if you want to pause and write down that statement right there. And then down here, here's an explanation of what's going on. So we didn't have to graph it, but if you graph this function out, you'll get something that kind of looks like this. And you'll see there's that 2417, nice smooth curve over here, vertical tangent to it. But right here at that other one, where it was t equals that 2 number, right? When t equals 2, I get negative 8, 1. And in the graph at negative 8, 1 is a corner right there. Okay? We have a corner there, so you cannot have a derivative there. And so that's why we don't have a vertical or horizontal tangent at that 2. Okay? So it pans out in our graph that we had. Now let's look at the second derivative. This one has caused a lot of problems for people, so pay attention. This is why I asked you to write it the way I did. So here's our definition. Look closely at it. If I give you these two functions as parametric equations with the parameter t, the second derivative of y with respect to x twice is the derivative of dy dx over dx. Okay? But I have to do this in terms of t. So I have to take the derivative of dy dx with respect to t and the derivative of dx with respect to t. We already have that to get to here. This will also be a function of t right here. So I take the derivative of this with respect to t, and again the bottom with respect to t. So this is what caused a lot of people, they think they just got to take the derivative of this right here and you're done. That's not the case. It's the derivative of that divided by the dx dt again. Okay? So remember, you did a dy dt over dx dt. You get this. Okay? Then we're going to take the derivative of that with respect to t, and then divide it by dx dt again. And you'll see that in the next example I'm going to show you right now. So here we go. So here's the parametric equations. X of t is 3t squared, y of t is 2t to the fourth minus 5. Find the second derivative. Okay? So to find the second derivative, you've got to find the first derivative, so start with that. So dy dx is dy dt divided by dx dt. Dy dt is going to be 8t cubed. Dx dt is going to be 6t. Reduce this, please. Make your life a lot easier. So that is dy dx. Now we want to find the second derivative of y with respect to x twice. And so to do that, this is how I recommend that you write it. To take the derivative of dy dx with respect to t, and then dx dt on the bottom. Take the derivative of this with respect to t, so that's going to be 8/3 times t, and divide it by dx dt again, which you already had right there. That's 6t. Then you work this out and you get 4/9. That is the second derivative there. Okay? Don't forget to put the dx dt in the bottom. Okay? So let me take a moment here and let you write those down. Let me put it right there for you. So you can copy that down if you need to. And then we'll do some more examples. Alrighty. Here's another example. Here's some parametric equations. We got t, x of t is tangent of x. Y of t is the sine of t. And this should be a t, not an x. The tangent of t. Sine of t. There we go. Much better. Find what is the second derivative of y with respect to x twice when t is equal to pi over 6. So we're going to do an evaluation. So we still do the same process. You have to go through the derivative. So what is dy dt divided by dx dt? You work that out. The derivative of y is going to be the cosine of t. The derivative of the tangent is secant squared of t. Try to simplify things out when you can, especially using identities when you have trig stuff, if it helps you out. This right here is 1 over cosine squared, so when I flip it over, I get the cosine of t to the third power. So it makes it a lot easier. I don't have to do a quotient rule for the next part. So the next part over here, we're going to find the second derivative, y with respect to x twice, which is the derivative with respect to t of dy dx divided by dx dt. Again, I recommend you write this out every time you do it. So what is the derivative of this with respect to t? So follow your process here. We'll take the 3 out front. You'll have the cosine of t squared. Chain rule times the derivative of that. Root cosine is minus the sine. And then dx dt, we already found the derivative of that. Then we have a secant squared on the bottom again. Okay? And you can leave it like this, or you can clean it up. Again, this is that 1 over cosine squared, so I can flip it over and combine it with this one right here. And that gives me a negative 3, the cosine to the 4th power of t times the sine of t. And I want to evaluate that when t equals pi over 6. So you just now plug in pi over 6. Negative 3 times the cosine of pi over 6 to the 4th power times the sine of pi over 6. Okay? And you can work this out and get your answers. Here's negative 3. The cosine of pi over 6 is the square root of 3 over 2. That's to the 4th power. And the sine is 1/2. And you can work this out and get an answer here. You're going to get negative 27 over 32. Double check my math, make sure that's right. And there you go. All right, let's take a look at some more examples. We're coming up here, two more examples. And here we go again. What we use second derivatives for concavity. So here we go. Here's a parametric equations again. Find the intervals for t for which the graph of the parametric curve is concave up. So I need the second derivative, so we go through the process again. So dy dt, dx dt. So the derivative of this is going to be 3t squared minus 4. This will be 2t. Again, you might want to consider cleaning this up. It's a lot easier if it's not in quotient form. This is a monomial, so it's easily divisible on each term up on top. And you'll get 3/2 times t for the first part. And this over here gives me a negative 2t to the negative 1. It's easier to take that derivative again. So what's the second derivative of that? With respect to x twice, it is the derivative with respect to t of this divided by dx dt. So I'll take this derivative. So I get 3 over 2, 2, t to the negative 2 over 2t again. And then you can clean all this up and work this out. 3/4 over t plus 1 over t cubed. You can leave it like that, or you can make it into a single fraction, depending on your needs and what you need to do with it. Just bring them together as one fraction. And why? Why would I want to do that, something like that? Because I have to determine when this thing is equal to 0 or undefined. So when is the second derivative equal to 0 or undefined? When is that occurring? Well, it will be 0. The second derivative of y with respect to x squared twice equals 0 when 3t squared plus 4 equals 0, and there is no real solution here. So there is no value where it's equal to 0. When is it undefined? It's undefined when 4t cubed equals 0 or when t equals 0. So that gives me a possible point of inflection right there. Remember, we did a little number line thing, and we're taking the second derivative of this thing, and we take this and we plug it in values bigger than 0 and less than 0 and stuff like that. Okay, so if I do that, I pick a number over here that's big, everything here is going to be positive, so that's positive. If I pick negative numbers, The top will always be positive, the bottom will be negative for negative numbers, so I have that right there. Okay. This is just tells me what I need, how I need to write my answer. So my answer then is the graph of the parametric curve is concave up on the interval of t 0 to infinity because the second derivative of y with respect to x twice is positive there. That's what you want to say. Okay? And I'll go ahead and show you the work that I had over here so you can pause it and see why. So if you look right here, you can see I gave you the, it's not part of the question, but I showed you the graph of that function again. And you can see that from 0 to infinity, that's the part that graph that, it's concave up. And this part was the negative side, and that was concave down. Okay? And so, there you go. You can pause and copy it all down. And the last little bit we have here is the arc length of a parametric curve. So this is a variation, an extension, I guess, if you want to, from the arc length that you found in rectangular form, which is this formula right here. Okay, this is what you used earlier to find the arc length along a curve. Now this curve is going to be represented by parametric equations, x of t and y of t, for t between a and b. And so this part right here, you don't need to memorize this. I just showed you how the formula we're going to use is derived from this formula right here. Okay, so this right here is f prime of x, just written as dx dy dx. And then parametric form, this right here becomes that. And so I have two terms in here, so find a common denominator, which is what this is. This is this thing squared and that thing squared. And so this will be the dx dt quantity squared and to make the 1. Okay, so pause here, I'm going to change the paper. All right, and so then where do I go from there? There we are. So this right here becomes this. So I put the two fractions into one fraction like so. Okay. And so then I have this situation right here. I have a square root going on. I got a dx out here. Okay. So if I simultaneously take that dx, divide it by dt, and times by dt, okay, it's like nothing happened. These reduce out. Okay, then I can take this quantity and put it back underneath here and leave just the dt outside. When I take something out here of a radical, a square root, and I want to put it back inside, I have to square it again. And so what happens is that becomes dx over dt squared. Okay? And so that quantity will divide that quantity out, leaving me this right here, which is our formula that you're going to use for parametric, to find the arc length of a parametric. Okay? So, that's how it is derived. You just need to know this formula to find the arc length of a parametric. Okay? So you see it's very similar to what we had before, only now we just have a dx dt, dy dt, and remember, this is based off the Pythagorean theorem anyway, so it shouldn't look that difficult in doing. Okay? So we have one more example to do, and that's showing you how to use this formula right here, which is pretty straightforward. So I'll find the arc length of a curve graphed by this parametric equations. X of t is t cubed, y of t is t squared on the interval from 0 to 2. And you couldn't see any of that, so there we go again. Okay? So, what do I need to know to use the formula? Well, I need to know dx dt and dy dt. So let's go find dx dt. and I get 3t squared. And I need to find dy dt, and that's going to be 2t. And so I have my formula for the arc length on the interval from 0 to 2. It'll be a square root of 3t squared squared 2t squared dt. Okay? So everything up to this point now is working this out by hand. You can also, at this point, if it's on the calculator version, type this into your calculator and let that give you the answer. But here's how you can do it by hand, so you can see how that can be done if you need to do something like that. There's some simplification techniques that help you out. Some things you should know that you can do if you've never seen it before. So I just powered that out. And I notice that I have a common factor of t squared in this. Okay? Since I have a common factor of t squared, I'm going to factor it out. And then I'm going to split the radical. So this becomes 0 over, I have the square root of t squared times the square root of 9t squared plus 4 dt. So I split that out. And then that right there just becomes t. So now I have, from 0 to 2 of t, 9t squared plus 4 dt. And this set me up to become u substitution. So if u is 9t squared plus 4, then du is going to be 18t dt. And there's the t and the dt. I just need the 18. And so we know that's going to be 1 over 18 du is t dt. And I'm going to be using that in the substitution. When t is equal to 0, u is equal to 4. When t is equal to 2, u is going to be equal to 9 times 2 squared plus 4, which is 40. So doing our u substitution on this, we're going to end up with, from 4 to 40, 1 over 18, u to the 1/2, du, and then I can work this all out. And then raise the power 1, divided by the raised exponent, and we're going to evaluate from 4 to 40, and do some simplifications and stuff like that, just to make it a lot easier to do. And then you plug in the upper minus the lower, so 1 over 27. Here's the upper, is going to be 40 to the 3/2, and then the lower 4 to the 3/2. Okay? And then I can simplify this even more, and what I want you to do is I want you to try and simplify this out yourself and see, can you get this answer right here? Tell me, try and get to this answer here. It's not necessary, you could leave it there, but this is a simplification to this point right here. See if you can take this and get to that. So that's what I want you to try and do. But again, I can also use a calculator, and if I did the calculator, I should get this answer right there. Okay? So that's going to be the end of this. I just need to put this over so you can see it. So here's the last example, and again, can you get that answer right there? And the last little bit, as you'll see as we move along, the arc length of a curve is often synonymous with the phrase, the distance traveled by a particle on a curve. So you will probably use this in that fashion on the AP exam. They'll ask you to find the length, the distance traveled of a particle along a certain curve, and this is the formula you're going to use for that parametric or vector form. Okay? And so that concludes this video, and we'll take questions in class.